Hello everyone, I'm Minsa Jung, the organizer of GDG on campus 성균관대학교 chapter. First, I'd like to express my gratitude to all students attending the 64th session of 글로벌IT전문가와 킹고인과의 만남. Today's lecture is titled A Beginner's Guide to Machine Learning with TensorFlow and PyTorch and will last approximately 1 hour. Our speaker, Mr. Bakshi, is an AI and software architecture at IBM and a recognized Google developer expert in machine learning. He has been selected as one of the LinkedIn's 25 tech influencers. With his passion for technology and this expertise, Mr. Bakshi is here to make machine learning accessible for everyone. Let's begin today's lecture. Bakshi, are you ready?
Screen. Give me just a moment, and we'll get started. All right. So, as mentioned, today I want to dive into the world of machine learning and AI, and I want to keep today fun and interactive. So I want to dedicate some time towards the end today for questions. Feel free to keep any questions you may have towards the end. We'll go ahead and discuss. I want to hear your thoughts. And of course, feel free to also follow along in real time if you'd like. If you're unable to sort of follow along in real time, all the code that I show you today, because I do want to get into some real world examples, will be available on a GitHub repo later here. I'll provide the link as well, so you can take a look at it afterwards too. But yeah, diving right into it really quickly, to give you a quick introduction for who I am and why I'm here today. As mentioned, my name is Tanmay, and I love technology. I mean, for the past 16 years, my passion has lied at that intersection of innovation and technology. I love applying tech like AI and machine learning to solve real-world problems, and also love to provide the resources to enable more people to use technology to solve the problems they see in the world as well. And so, when I say that I love to have fun with technology and that really excites me, I really do mean it. As a matter of fact, pretty much the only thing I can remember loving as long as I've loved tech is probably McDonald's. And I know that sounds completely irrelevant, but it's actually relevant to the world of tech, because back late last year, I actually got to visit the McDonald's headquarters because of a project I was working on at IBM around using AI-powered conversational agents to automate the McDonald's drive-thru. And so I've even gotten to merge my passions of like fast food and technology, which is really fun. And so it's really representative, I think, this project of one of the things that I love so much about AI, which is just how universally applicable it is. At the end of the day, machine learning effectively just boils down to being able to automatically find really complex patterns in data. And data is generated everywhere, and so machine learning is effectively universally applicable. And what I mean by that is the same foundation innovations we had to come up with in order to, for example, power this use case where we're automating the drive-through are going to be incredibly helpful in a bunch of other domains going out from here, when it comes to conversational agents, chatbots, and so much more. And so, as you can tell, I love the world of AI, but I admit that one thing I haven't been a fan of is just the term artificial intelligence. Through the journey I've had working with it, I've always sort of disliked the term artificial intelligence, because I feel like AI isn't an accurate way to describe the technology that we have today. In fact, I would say that AI isn't even really a tech term to begin with. Instead, artificial intelligence is really just the feeling that we have that is powered by a lot of the machine learning technology and machine learning innovations that we've seen recently. So a lot of the new advances that we call AI are really powered by the tech term machine learning, because ML is the actual specifics of techniques and algorithms that we use to power those innovations. Whereas, as I mentioned, artificial intelligence is really, at the end of the day, more of a user experience term, right? AI is more about what technology feels like, and it's about, it really is a moving goalpost. It changes over time as we come to expect technology to do or not be able to do certain things. I mean, maybe a couple decades ago, we would have considered, for example, chess engines and chess bots as artificial intelligence. But these days, we don't really call it AI anymore. Maybe in 2011, IBM Watson playing Jeopardy would have been our sort of goalpost for what artificial intelligence is. And now, I guess ChatGPT is the de facto standard for what people think of when you say artificial intelligence, right? And that's basically a unanimous answer that I get from almost everybody when I ask, what's the first thing that comes to your head when I say AI, is it's usually ChatGPT. And so there's a lot of hype around this technology, and there's a lot of misconceptions as to what it can and can't do. And the industry is starting to realize a lot of those misconceptions. As a matter of fact, I remember reading a report from Goldman Sachs back in June of this year, where they said some things that even I sort of had to take a second to think about and at first disagreed with. But then I realized that they're actually right. And one of the things that they said was that AI's killer application has yet to emerge, right? So there's still a lot of untapped potential. But at the same time, AI technology is exceptionally expensive. And to justify those costs, the technology must be able to solve complex problems, which it isn't designed to do. And when I read this piece at the end, AI must be able to solve complex problems, which it isn't designed to do. At first, I was kind of taken aback because I really had to think about that. I mean, what's the point of AI if we're not using it to solve complex problems? Why does it exist? But then when I really thought about it, I realized that, well, actually, they're right. At the end of the day, if you take a look at the research path that brought us to where we are today, especially with generative AI, it actually wasn't meant to solve the kinds of complex problems that we're trying to get it to solve these days. A perfect example of this is a research paper from back in 2017, which in my opinion is actually what started the sort of, I guess, butterfly effect that led us to where we are today with generative AI. It's a paper by OpenAI, and it has one of my favorite lines in machine learning research. So let me tell you what they did in this paper. What they did is they trained a super simple machine learning to generate Amazon reviews. Right? And so what this model would do is it would take a look at a series of characters from an Amazon review. The job was to predict the next character in the review. And the theory is that if the model can predict the next character in a review accurately enough, then it can also generate these reviews. Because then what you do is you start from nothing, you have it predict the first character, put that in the sequence, have it predict the next one, and so on and so forth, until you're done, until you've actually you've generated an Amazon review. And the actual research here doesn't necessarily have an immediate real-world use case, because what's the point of a model that can just generate Amazon reviews? But here's the really interesting thing. If you take a look at OpenAI's report from this research, you'll notice one of the lines they have here is, "We were very surprised that our model learned an interpretable feature." So what does that mean? Well, what OpenAI discovered is that simply by training a model to predict the next character in an Amazon review, so just on Amazon review generation, based off of a training objective, based off of that goal, the model automatically learned internally a single linear numeric representation of the abstract concept of sentiment. And so what that means is that even though the model was never trained to understand what good sentiment or bad sentiment is, like a good or a bad review, that was never its objective. But just based off of learning to generate them, it had automatically learned that internal understanding of the abstract concept of sentiment, what good and what bad mean. And so OpenAI researchers thought, well, what if we scaled this? What if we trained much bigger models on way more data? Could they theoretically understand even more abstract concepts about the world? Could they understand this data really well by learning through generation? And this is what led them to use a bunch of new advances in the machine learning industry, including, for example, the transformer architecture by Google. And they released the next paper, Improving Language Understanding by Generative Pre-training. GPT, generative pre-training. And when they released this paper is when things really changed, because they realized that, yes, when you do in fact scale this technique, you get models that can understand the world very, very well. But what that really means, though, is that at the end of the day, generative AI was developed as a means to an end. It was never really meant to generate. It was instead meant to work towards better AI models with a much richer internal comprehension of the way that the world works and the way that data is structured. Effectively, we wanted to build AI with a rich internal world model, is what it's called. A model that understands the way the world works really well. And then, OpenAI continued to scale it further and further and further. And eventually, with the release of their GPT-4 model, is sort of when things really started to change, because suddenly they had these benchmarks proving that GPT-4 was significantly better than a bunch of other, state-of-the-art, or at least previously state-of-the-art models for specific domains and specific tasks like common sense reasoning and code generation, even though those models were trained to do those tasks, and GPT-4 was just trained on generating tons and tons of text. And so this technique proved to be really valuable. And all of these advances on what we call generative AI technology today really all stem from those core innovations in machine learning technology that were originally intended for comprehension and understanding. And so that is why I think it is really, really important to understand all the fundamentals and the principles behind machine learning and really any technology that you develop with. It's because it's those same fundamentals that scale into significantly more complex use cases and more complex outcomes and applications. You can build those applications in ways that are much better and more nuanced and useful if you have a more principled understanding of the basics that are powering them. And so this finally gets into the really interesting part of today. How does deep learning work? And we're going to take a look at some real in action today. I want to show you how you can actually get started yourself. Really quickly, though, I want to start off with just a primer on what the core ideas behind deep learning and machine learning actually are. So to start off, I want to reference a joke. It's a joke about topologists, and topologists are mathematicians that specialize in studying topology of spaces. And the joke goes like this. A topologist can't tell the difference between a coffee mug and a donut because, according to the topologist, they're the same quote-unquote shape. They're the same topology. Because a coffee mug and a donut have one hole in it, and so by definition, mathematically, they're the same topology. Their space is the topology. And the reason I bring this up is because I want you to imagine you have a coffee mug. On this coffee mug, maybe you draw a bunch of random blue and red dots. So you draw a bunch of random blue and red dots on this mug. When you do this, most likely, if you just randomly put these dots all over the place, there won't be a way to use a single straight line to separate between the blue and the red dots because they're random, they're scattered. But what if the task was that you had to separate the blue and the red dots using a single straight line? Well, one of the ways you could do it is by taking the space in which those dots lie, so the mug, and transforming that space into some other shape, maybe, for example, a donut or any other shape that works, and transform it in such a way so that when you're done the transformation, the dots end up in clusters in little pockets of that space where you could, in fact, use a straight line to separate them. Now, the reason this is important and the reason that I bring this up is because mathematically, if you have data where you can draw straight lines to separate between your different clusters, then figuring out what those straight lines are is really, really easy. But the problem is that the majority of the kinds of data we want to work with are way too complex to use straight lines. For example, if we go back to the Amazon review generation use case, if you think about representing an Amazon review as points in some very high dimensional space, then most likely just taking the raw characters and putting them in that space, you wouldn't be able to draw straight lines in it to determine what the next character should be. It's a much more complex and sophisticated shape to that space. And the idea behind modern machine learning is that by using a bunch of different interesting mathematical techniques, you can figure out how you need to transform a space in order to make it so you can draw those straight lines. Because if you can do that, then you can figure out what those straight lines are, and that means that you can achieve the task that you want to. And as an example, here is a visualization of a very simple data set. The data set is called the iris flower data set. And it consists of measurements so 4 different measurements, like petal length and width and so on, of 3 different kinds of iris flowers. And so there's 150 data points. They measured 150 different flowers. And with these 150 measurements, which once again belong to 3 different species of flowers, if you plot out those measurements in 2 dimensions, they look like this. And so you can sort of see how the 3 different species are clustered into their own little groups in this space. And if you were to draw straight lines to separate between those 3 clusters, I mean, it would mostly work. Red is definitely separable. Green and blue would be a little bit inaccurate, but it would mostly be able to separate those 2 clusters. But the thing is that the data did not originally look like this. This is what the data looks like after having been processed. The original data looks like on the left. Now on the left, of course, the red cluster is still very easily separable. You can still separate that with a straight line. But then the green and the blue are significantly more intertwined. The job of a machine learning model is effectively to determine how you can transform the data from looking like on the left to instead looking like the data on the right, which is, of course, an incredibly difficult task. It's not easy to do that. But what you're looking at right now is the result of the transformation that was automatically learned by a machine learning model that I trained and that we will actually train together today, when it was specifically trained just to determine which species of flower the measurements belong to. So I trained a machine learning model to take one of these points and to predict which species of flower it belonged to. And then if I go back and I sort of take a look at internally within the model how it learned to represent the space in which these flowers lie, you realize that it looks like the data on the right, which is really, really interesting to me. And the reason it's so interesting is because this exact same technique, which looks really simple for iris flowers, if you scale it up to maybe billions of parameters instead of just a couple hundred parameters, at billions of parameters large, even though this is the same thing you're doing, suddenly the emergent capabilities of those models are generating language and being able to classify images really well and so on and so forth. Like for example, if you built a neural network to classify between images of cats and dogs, then what you're effectively doing is you're taking an image and you're running it through some series of sophisticated layers, and these layers are processing the image and finding different features within the image. And all of this is working towards being able to do a single linear classification, drawing a line in some space to determine whether the image belongs to the cat cluster or to the dog cluster. And what you're effectively doing here is you're taking this whole sort of head of the model, the first part of it, and you're using it to transform your image into what you call an embedding space. This is the part of the model that's able to take your image, your input, and bring it once again into a space where it is linearly separable. And then finally, all you're doing is figuring out which cluster your data belongs to. Effectively, that's your training objective. Your training objective is to say, given the final representation of this input data, what category does it belong to? But that's just one of the many possible training objectives you could have. For example, you don't just need to say, or you're not forced to say that your input has to be classified into one of many different categories. You could, for example, provide the model with 3 different inputs: an anchor input, a positive input, and a negative input, where the positive is more similar to the anchor than the negative. And you could optimize the model to keep the anchor and positive closer together in space and the anchor and negative further apart in space, right? There's many different ways that you can sort of massage the training objective so that you get the model to learn the kind of space that you want it to learn for the specific task that you have. So that's a quick primer on some of the core concepts behind machine learning and some of the intuition, but I know that that was a lot and it probably won't make a lot of sense until we dive into the actual code and take a look at some visualizations. So without any further ado, let's take a look at it. What I want to do is I want to start off with a quick primer on machine learning libraries just in general. So what I've got open right now is a tool called Google Colab. Google Colab is really useful. I'm not sure if you've used it before. As a quick primer, it allows you to run Python code on Google's infrastructure. So you can use, for example, Google's GPUs and TPUs for free to like train machine learning models and experiment with Python code. And we're going to use it today to build our own little ML experiments. So the first thing I want to do is start off by covering just a quick primer on how libraries like PyTorch and TensorFlow work and what they allow you to do. So in general, if you take a look at most of the descriptions for these frameworks, you'll notice that they're usually summarized to machine learning frameworks. So PyTorch, for example, is usually considered a machine learning or a deep learning framework. But I don't actually think that that is the most accurate way of representing it. Instead, I think there is a more fundamental series of a more fundamental set of two capabilities that these frameworks give you that are really powerful. One of them is the ability to accelerate your compute on really specialized infrastructure. So, for example, if you're training really big ML models, like OpenAI's GPT or Google's Gemini, these models have billions of parameters, and in order to run them efficiently on really specialized hardware like GPUs and TPUs and so on, you need a framework that's able to do your matrix multiplications and your other mathematical operations really fast on that hardware. PyTorch and TensorFlow, these sorts of libraries, they let you sort of not worry about that. You just tell them, hey, move this array to this device and run this math, and it'll figure out how to perform those mathematical operations on the hardware that you specify. But the other interesting capability is what's called automatic differentiation. Now, the way that machine learning works, one of its core sort of constructs is the idea of gradient descent. Gradient descent is effectively using calculus, which you don't need to have too much of like a calculus background for today, but it would definitely help. I'll try and simplify this as much as possible here. Effectively, what these libraries let you do is automatically compute function derivatives for the operations that you run. As an example here, I'm going to go ahead and in Google Colab run import torch to import the PyTorch library. And before we use PyTorch, I'll just do one quick baseline example. Of course, in Python, just like any other programming language, you can do arithmetic. So if I do this, then of course Python will give me the result of x times y, which is 30, because 5 times 6 is 30. But what PyTorch does is it implements the same kind of math that Python does. Just it wraps that math in an object that it calls a tensor. So for example, what I can do is I can tell PyTorch that I want to create two tensors, we'll call them x and y again, and they have the values 5 and 6. And at first, it seems like PyTorch isn't doing much because, I mean, Python was already doing this. Why did I need PyTorch, right? But there's actually something really special going on here. You just don't see it at first. And let me show you. If I take this same code here, and if I take the result of this and put it in another variable called z, and I do one more thing, I pass another parameter here, requires grad equals true. Then what happens is PyTorch, what I'm telling PyTorch is that whenever these tensors are used for some kind of mathematical operation, PyTorch is supposed to internally note down every operation that occurs. And when PyTorch notes down all those operations, it constructs a large graph in memory. And that graph is used to figure out what operations you ran. And using that graph, PyTorch can then automatically compute the derivative of those operations with respect to any one of the variables that you use within those operations. So, of course, running this, print z, still prints 30. But now, if I run z.backward, then if I print x.grad and y.grad, this should theoretically print 6 and 5. And the reason it should do that is because the derivative of the function, the derivative of this function with respect to x is 6, and with respect to y is 5, because of the way that derivatives work for multiplication. And there we go. PyTorch was able to do that for me automatically. I'm saying, here's the result of my function or my series of operations, run a quote-unquote backward pass on it, which means go and compute all the derivatives, the gradient. And then because I ran this, and because I told Torch that I require gradients, it automatically gives me gradients. And at first, that doesn't seem like it's all that special, but when you think about it, and especially, I mean, you're about to see what I mean, boils down at its very core to those two simple things. It is being able to accelerate matrix operations and math across really specialized hardware and being able to compute gradients and derivatives of very complex functions. If I had to manually write the derivatives for all my machine learning models, it would be way too much code. It's not practical. These libraries do it for me. So really a more accurate way to summarize what these libraries do is not necessarily that they're machine learning frameworks per se. They're more mathematical and I guess scientific computing libraries that also support acceleration of math on hardware. So with that out of the way, I want to move into, I guess, my first real world example of some of the intuition behind ML. Before I do that, I'm just going to make sure, okay, there we go. Yep, still screen sharing everything, just making sure you can still see me? Okay. So what I want to do is cover an example of what I like to, well, so what I'm going to cover here is an example of a technique called trilateration. So I'm not sure if you may be familiar with the concept of triangulation and trilateration. Triangulation is the way the GPS works. So when you, for example, open up Google Maps or any other sort of GPS, the way that the GPS receiver determines where you are is by connecting to at least 4 different GPS satellites. Now, these GPS satellites know where they are in the Earth's orbit. Because the GPS satellites know where they are, and because your GPS receiver knows its angles to those 4 GPS satellites, right? Because so your receiver knows the orientation to those satellites know where they are. Using your angle to the satellites and the satellites' positions, you can then determine where you are. And so the ability to determine where you are is based off of those other reference points. Now, triangulation works on angles. Trilateration works on distances. And so similar to how you need angles to satellites to figure out where you are, the idea behind trilateration is that you have reference points, you know your distance to those reference points, and based off of that distance, you want to be able to figure out where you are in the space. As a quick side note, mathematically, just the way that this works is if you are in some n-dimensional space, then determining your location within that space using trilateration or triangulation requires n+1 reference points. So we live in a 3-dimensional universe. We have the XYZ dimensions. And because of that, you need 4 GPS satellites to determine your location because you need +1. Similarly here in the show you dimensional space performing trilateration, and therefore you need 3 reference points. And that's exactly why you see these 3 points in the space here. So let's quickly dive into this example. As you can see, I've got 3 different reference points. They're A, B, and C. And let's just say, for example, there's we are a point in this 2-dimensional space. So we're a point in this space. And we don't know where we are. But we do know the distance from us to these 3 reference points. In particular, say that from point A, we're 4 units away. From point B, we're 10 units away. And from point C, we're 5 units away. So 4, 10, and 5 units respectively. Now, one of the really easy ways to visualize where we are in the space is to draw circles around the reference points, where the radius of the circle is the distance from the reference. And where all 3 circles intersect is where we are. So for example, starting from A, if I draw a circle with a radius of 4, somewhere on the sort of edge of this circle is where we're located. We know that for sure because that's how far away all points from A are. If we also draw a circle around B, suddenly there's 2 intersecting points, and that means that we have to be either at this location or this location. And then drawing one more circle, you see there's only a single point where all 3 of them intersect, and so that's where we have to be located. And so that's how we know that the sort of point that we're located at is x equals 2, y equals 2. But how are we supposed to determine that mathematically instead of like actually drawing circles? Well, there is a way to figure it out using linear algebra, but there's a more interesting way to figure it out, in my opinion. And the more interesting way is to use the same kind of math that you use behind machine learning. And that's why I'm showing you this example here. It's because you can actually solve the trilateration problem using the exact same underlying math and techniques that power machine learning models. In fact, so much so that you can use PyTorch to solve trilateration even though that's technically a machine learning framework. And the way we do it is by optimizing our guess of where we are in the space. So effectively, what we do is we reframe the task. Instead of saying, we know our distances, where are we? Instead, we say, okay, let's guess where we are. Now, at first, most likely our guess will be wrong, and it'll be very wrong, right? But if we have a guess, and if we know where the reference points are, then we can compute the distance between where we guess we are and the reference points. We then have the observed distances from where we guess we are to the reference points, as well as the known distances, because we do know how far away we are. If we compare those distances with each other, and we attempt to minimize the error, make it so that how far away we measure the guess is from those references versus how far away we are, match each other as closely as possible, eventually, when they match each other exactly, that means our guess is where we are in the space. And the really fun part here is that Desmos, this online graphing calculator, recently introduced three-dimensional support here. And so I can actually visualize for the first time ever, because I've loved using the example of trilateration, but now I can actually finally visualize what that error function looks like. So what I've got here is this error function that I've defined. I'm going to go ahead and expand this really quickly. And as a matter of fact, technically, I guess it would be probably useful to divide this by 3 here, so it's easier to take a look at the thing in scale. But effectively what this function is doing, E1, is it takes a point G. So it takes some x, y coordinates, and we're calling it point G. And we compute the distance between that guess, G, and the 3 different reference points, A, B, and C. So you can see over here, we compute the distance between G and A, the distance between G and B, and the distance between G and C. Given those distances, we compare them by subtracting out the known distance, because once again, we know we're 4 units away from A, 10 units away from B, and 5 from C. So the distance to A minus 4, distance to B minus 10, distance to C minus 5, and then all those distances are then squared because we don't want it to be a negative number. We want it to be a positive number, and we want to sort of amplify the difference between between what we guessed and what we know. And then we get the average. So this function here is called the mean squared error function. It's effectively, because we're getting the average, squared error, right? So mean squared error function. Now, if I go ahead and visualize this in 3 dimensions, you'll see that the function looks a little bit like this. It's sort of this, cone almost, where the function has incredibly large values everywhere in the space except where the circles intersect. Its lowest point, the global minimum of this function, is at x equals 2, y equals 2, which is that point where all those 3 circles intersect. That's sort of like where we are in the space once again. But you'll also notice that there are these sorts of almost like crevices, I guess. If I sort of zoom out, like for example, right there, you sort of see how there's this local minimum where the function value is pretty low, but it gets much lower below. And that's because this is a point where, for example, 2 of these circles intersect, but not 3 of them. And the goal of machine learning, and the goal that we have here, is to use this error function in order to figure out where we are by moving to where the error function is lowest, because that's where we are located. When the error function is 0, that means there is no error. Our guess is correct. We've found where we're located in the space. And as I mentioned before, you can have all kinds of different training objectives. You're not just limited to, these standard kind of objectives. For example, here, I made the decision to square the errors because that's a standard way of doing it. But instead of getting the square of the errors, I could also just get the absolute value. It doesn't emphasize the errors as much, but it still solves the problem of having negative numbers. If I visualize that, you can sort of see the difference in the way that error function looks. You can actually see how there's physically these sorts of indents in the space based off of the different circles intersecting, and how all of it sort of moves down towards this global minimum in the center here, where x equals 2, y equals 2, because then the guess is perfect. And so once again, sort of what all machine learning models are trying to do is reframe any complex problem into a problem where there's an error function that is capable of taking some guess and taking your inputs and outputs and determining a scalar individual numeric value of how bad your guess is, so that you can use calculus to figure out how to move your guess in such a way to minimize the error, thereby bringing you to the values that you expect. That is the core of all ML, and it's actually pretty elegant that when you scale this up from 3 dimensions to tens of thousands to hundreds of thousands of dimensions, you get incredibly interesting emergent behavior, like being able to understand language. Trilateration is a wonderful example of that sort of those core constructs, which is why I've got a Python notebook here that demonstrates how to use PyTorch to implement trilateration. So I want to quickly go through this, and then we'll get into some more machine learning related examples in particular, and train some actual models, including one on some real healthcare data, which I think is really exciting because it shows off just how easy it is nowadays to build real ML models. So this Python notebook over here, once again, it's available in the GitHub repository that I'm going to share, implements trilateration using PyTorch. So I'm going to go ahead and start off with just a few simple imports. And we're going to start with this function over here. This function is called trilateration loss, and it implements the error function that you see over here. So E1, which computes this mean squared error value, this sort of like compute is done by this Python function. The way that it works is it takes your guess. The guess is 2-dimensional, so it's an x and y coordinate. And the type of it is a torch tensor. So we're taking the PyTorch representing the guess. We're also taking a tensor containing the reference points. So in this case, we expect 3 reference points. So the shape of this matrix will be 3, 2, because there's 3 reference points with x and y coordinates. And then we're also taking the distances. These are how far away we know we are from the reference points, so we can figure out our error of the guess. So what we do is the first thing is we compute the guessed distances. And the way we do this is simple Euclidean or straight line distance. So we take the reference points minus the guess. So for the x and y of each reference point, you get the difference between that and the guessed point. You square those differences, you get the sum of those squared differences, and then you get the square root, which once again is exactly what we're doing here for our distance function. So super simple straight line distance function. And then from those guessed distances, we take the guessed distances, we get the difference between them and the known distances, which is, once again, how far away we know we are in the space. We square those just like we did in Desmos in the graphing calculator, and then we get the sum of those squared differences. So the theory is that if the guess is actually where we are in the space, then the guessed distances will be equal to the known distances. And if the guessed distances are equal to the known distances, oh, sorry, didn't mean to add those there. If the guessed distances are equal to the known distances, then the loss will be 0. If the loss is 0, that means the error is 0. That means we've found exactly where we are, right? So there we go. We're going to run that function. And then we've got another function. This is what actually implements the core trilateration logic. The way it works is by once again taking the reference points and the distance, and then 2 extra parameters that I'll explain in just a moment. The way this function works is it starts by creating a guess. So it starts by quite literally just saying random numbers, 2 random numbers, a random x and a random y, and that's where we're starting. And we print out what that starting guess is. Then we instantiate something known as an optimizer. The optimizer is the specific technique that we use to actually move in that space. So if I go back to the graphing calculator here, imagine we started with a guess that was somewhere over here. When we guess this, the sort of process we go through is the process of gradient descent, which is step by step, iteratively, we slowly want to move that guessed point down further and further towards a minimum until we reach the global minimum, which is down here, which means we found our actual location. Now, when we're starting all the way up here, we have to have some kind of math that tells us where to move next. And the technique, the actual the algorithm you use for determining, hey, I'm over here and I know my function value, where do I go based off of what the function is telling me? Figuring out where you go, and I guess technically what's called figuring out how to step in the space, that's the job of the optimizer. We're using an optimizer called SGD, or stochastic gradient descent. This is the simplest kind of optimizer, you don't necessarily need to worry about why it's called stochastic gradient descent. We can get into that later. But it implements the simplest form of this kind of optimization. And this is a construct that is provided by default by PyTorch. PyTorch has a whole series, it has a whole package called the Optim package that contains a bunch of different optimizers. Stochastic gradient descent is one of the many optimizers they provide. And as input, the optimizer requires a list of things to optimize. In this particular case, the only thing we wanted to optimize is the guess. So that's the only parameter that we pass it. Apart from that, it takes an additional parameter, and that is the LR, learning rate. So the learning rate defines for the optimizer how big the steps should be that it takes. So coming back here, if you take a look at the way that the way that the optimizer figures out how to like where to move in the space, it's using the derivative of this function with respect to x and with respect to y. But then using the derivative, which tells you the direction to move for steepest ascent, which then inverted tells you the steepest descent direction, knowing how far to step based off of that is something that we have to define using this learning rate parameter. Because the problem is that, for example, if maybe the guess was really close to the sort of best point here, if it was really close, and we know that we have to sort of move down in this direction, if we want to move in that direction, but we go too far, then we end up overshooting it and we sort of end up back on top over here. We don't want that. We want to end up here. And so you want a learning rate that is high enough that you don't take way too many steps to move down towards this best solution, but a learning rate that's simultaneously low enough that you don't end up getting near the solution and then just overshooting it and never actually being able to hit the solution. And this is where machine learning can sometimes, in practice, end up being a bit more of an art than a science, because there's not necessarily like one universally best way of determining what that value should be. It's just there are better and worse values for certain tasks. In this particular case, a relatively low learning rate like 0.01 works just fine for this particular task. And then, of course, you also have to have a number of iterations that you're willing to take in the space. Now, technically, for this particular task, because it's a very simple one, we could just say, okay, we're going to keep optimizing, we're going to keep stepping in the space until we've reached a perfect solution. But in the real world, for most machine learning tasks, there is no perfect solution. And so you have to have some sort of like number of iterations, number of steps where you say, okay, once we reach this point, we'll sort of call it and we'll see how well the model works. In this case, I'm capping it at 1,000, and however, like wherever we end up in the space after 1,000 steps is what we're going to get. So the way the actual optimization logic works is actually pretty simple. We start off by telling the optimizer to zero out the gradients. So this will make it so that if there are already any gradients that PyTorch stored, it just resets them. So this is just resetting state. That's it. The next thing we do is we compute the error. So we take the guess, we take the reference points, and we take the distances, and we use that to compute the loss. When we have the loss, that means we know how bad the guess is. Because we know how bad the guess is, we can call backward to compute derivatives with respect to all variables. In this particular case, it'll compute with respect to the guess, and then we tell the optimizer to take a step in the space. The optimizer will then use the gradients on top of the guess that we passed it, and it will use those gradients and use the learning rate to figure out how do we move the guess. And it'll actually move the guess for us as well. And it'll keep doing this over and over and over again 1,000 times until it's done. Each time it'll keep printing out what the current guess is and what the current error is. And I also tell it to sleep a little bit because otherwise it goes so fast that you can't see it actually progress. And that's all there is to it. So reset state, figure out your error, do your backward pass to get gradients, step in the space, and do it all over and over again. It is really interesting how this is exactly what ML code looks like in the real world, and you'll see that in just a moment. So I'm going to go ahead and run this, and now we can actually run the function. So this is setting up the experiment the same way it was in the calculator. So A, B, and C are at the same locations they were over here. And these three different distances, 4, 10, and 5, are once again the same as what we had over here as well. So if I run this, in theory, it should start with a bad guess, and then slowly we should see it move that guess closer and closer to where the actual point is. So if I run this, well, the starting guess was actually not too bad, I guess, but you'll still see it sort of slowly work its way, moving both of those numbers closer and closer to x equals 2, y equals 2. As you can see, the y dimension is almost there already. X is getting there as well. And as it gets closer to 2, 2, the loss is going down further and further because the error is getting lower because, once again, the guess is getting better. And there we go. Only 200 iterations in, and we're already almost at 2, 2. And that is a quick demo of trilateration, one of my favorite ways to demonstrate the core math and logic that goes behind real-world machine learning models. This can then scale up into significantly more complex models. For example, over here is a model that performs iris flower classification. So the same data set that I was showing you previously with those many different clusters. This notebook over here, which is available on my GitHub repo, implements a very simple way of training a model to perform iris flower classification. The way it works is by using a bunch of the built-in PyTorch constructs to implement being able to load in the iris flower dataset because that's built into the scikit-learn machine learning library. And then down over here, let's see, okay, it's just launching the notebook. There we go. So as you can see, we are loading in the data set and we are able to visualize it with this logic over here. And it looks kind of similar in structure to the image on the left over here, just slightly different scaling. Now, given that, we want to train a simple model on this data. And the way that we do it is by telling PyTorch to create a simple model that takes the 4 measurements of each flower, projecting it up into a 5-dimensional space, then running what's called a multi-layer perceptron, which is a special kind of machine learning model. Specifically, it's sort of like it's a kind of neural network architecture. Effectively, this perceptron, this multi-layer perceptron layer, will take that 5-dimensional representation of the measurements, project them up 4x, so it'll go up to 20 dimensions, and then project them back down to 5 dimensions. And then from 5 dimensions, we go into 3 dimensions. These 3 dimensions represent the probabilities of the 3 different kinds of iris flower. And the hope is that if we can optimize this model end to end to go from the 4 measurements to the 3 probabilities, then internally it will figure out what the numbers need to be for all the different parameters in the model in order to transform those measurements into species probabilities. And the way that it'll do it is by making the data linearly separable at this particular layer. So the optimizer we're going to use here is a different one. We were previously using stochastic gradient descent. Now we're going to use Atom. That's not something that you need to worry about right now. It's just a different way of performing optimization. And it's better for real-world machine learning tasks that are more complex, where gradient descent sometimes is less stable. If anyone wants to learn more about that, feel free to ask me in the Q&A, and I'm glad to go into some more detail. But we'll sort of skip over that for now. Running that, PyTorch is able to construct the model for me, and the train model function that I've put together over here, which looks very, very similar to trilateration. You're resetting your optimizer, you're running through your model, you're computing your error, you're getting your gradient and stepping over and over again. You'll see that the model trains very quickly, and our loss goes from 0.8 down all the way to 0.06 pretty quickly. And those numbers probably don't mean much to you, but we'll go ahead and test the model now to get some more interesting numbers. So testing the model on the test data set, which is data that the model's never seen before, of 0.02, and already with barely any actual effort put into training, we're already at 100% test accuracy with this model. And the most interesting part is down here. If we go ahead and sort of manipulate our model a little bit, if I remove the last layer of the model, the part of the model that actually computes the iris flower species, and if I just look at the very second last layer of the model, and if I visualize what the outputs of the model are before the final output, you'll notice that the data is almost linearly separable, similar to this visualization that I had shown you here. And so just by learning how to actually classify these iris flowers, if you look inside the model and you sort of like skip the last little output, you notice that now the data is almost perfectly linearly separable. because that's the most mathematically effective way for the model to be able to perform the task that we're asking it to. And now, with this sort of core knowledge and fundamentals of machine learning, you can implement some really interesting use cases on top. For example, this is the last sort of notebook I want to run you through here. And also, by the way, if you run this notebook yourself, once again, it's available on GitHub. One of the things you'll want to do is click on the Runtime tab at the top, and then click Change Runtime Type, and then under Hardware Accelerator, click on T4 GPU. What this will do is it'll give you a special environment on Google Colab that has access to a GPU, which will accelerate the compute necessary for this particular task. And there's also a dataset that I provide with this notebook, the brain tumor dataset. It's from Kaggle. If I just pull this up here so you can take a look at it, it contains images of not this one. It contains images of brain MRIs. Yep, there we go. It contains about 100 of them with no tumors and 100 of them with tumors. And the idea is to train a model that can determine if there are tumors in these MRI images or not. And the really interesting thing about the way we're going to approach this problem today is we're not going to train a model from scratch, because that would actually take way too long. This is a very complex task. And there's also very little data. There's only 100 images of MRIs with and 100 images of MRIs without tumors. So we need to have a way of more efficiently learning whether or not an image contains a tumor. And the way we're going to do it is by using a pre-trained model, a model that's already been trained on thousands and thousands, millions actually, of images. In particular, the model has been trained to classify these images into one of 1,000 generic categories. It's a model that's been trained on generic image classification for tons of different categories, like different animals and different objects, people, and so on and so forth. This model has already gained a really good internal understanding of just how to recognize different features in images. And what we're going to do is we're actually going to freeze this model. We're not going to change the model itself. We're just going to take the internal activations of the model, kind of like over here when we stripped off the last layer of the iris flower classifying work, and we instead just looked at the second last layer and we visualized sort of the points in the space. So what we're going to do is, similarly, we're going to take a look at that second last layer of this pre-trained image classifier model, and we're going to try and take its representation of images, which are 768 dimensions, which, like, think about how big that is, because here we had a 5-dimensional representation of the iris flowers. Here we have a 768-dimensional vector representing the images that are sort of fed into this model. And we're going to use that to train the model to predict whether or not the image has tumors. And just like that, as you can see, as I run this cell over and over again, you can see that loss value going down in real time. Now, again, real-world machine learning models aren't perfect. Loss is going to go up and down. It's not like as smooth of a curve as you see here. Like, trilateration is so simple that the curves are smooth enough that you can follow it to a perfect solution. But again, there's no perfect solution here. There's room for error. But running this training loop over and over again, which follows the same pattern as before, you can see that if I run the evaluation down here, already in literally just a couple of seconds, we got a machine learning model with barely any code that is already 84% accurate on a testing set at classifying between images of brain MRIs that do and do not have tumors. And this is one of the really interesting things about ML, is that even though, you know, we just spent quite a bit of time going through, and there we go, 88%. Even though we just spent quite a bit of time going through all these little finicky fundamental details and it seems really complex, at the same time, the ecosystem around this tech is so mature that these days, you know, I could write just a little bit of code in a few minutes, and this code is already giving me 88% accuracy on what seems to be a pretty complex task with barely any data. And so that's one of the things that excites me about the world of ML. Yeah, now I would love to go ahead and hear from you and answer any questions you may have with the time that we have remaining. So hopefully this was helpful to give you an intuition for the way that ML and AI and the fundamentals behind it work. And once again, I would be glad to go ahead and answer any questions you may have now. Thank you. Thank you very much. You are mute. Oh, there we go.
Thank you, Tamei, for such an insightful lecture. I believe many students have gained valuable knowledge through today's session. On behalf of everyone, I extend my heartfelt thanks to Mr. Bakshi. This concludes today's event. Thank you, everyone.
Thank you. Thank you. I see a question in the chat. Can we address that now? Do we have a minute to
Yes,
go through
we can
that?
answer questions on the chat for right now.
Perfect. Thank you. Okay, so the question I see, as you mentioned, the rise of generative AI and ChatGPT has changed the AI landscape again. How do you think AI will develop after that? Let's see. I mean, I think the main thing that will really evolve when it comes to AI in the future, or at least in the near future, I think, is the AI is going to become more scalable. One of the big problems with the way that modern ML advances work, like GPT or Gemini and so on, is that they're incredibly inefficient. They do work, but the only reason that they work is because we train really, really big models on tons and tons of data, and they just end up being able to gain these emerging capabilities because gradient descent is good at finding them. But the problem with it is that every request you make against GPT, you're using a lot of water, a lot of electricity, and training the models is becoming unsustainable at this point. We might physically actually not even have enough data to train the next biggest models, right? So I think one of the things that's going to have to improve is the efficiency of the way that these models are trained and the way that they're evaluated and so on. Additionally, I think explainability and being able to sort of crack open the black box of machine learning is going to be really important. Like, for example, with the technique that I covered today around, say, iris flower classification, right? Even with something as simple as that, it's easy to see how end-to-end the math is effectively just implementing a bunch of matrix multiplications and we just optimize it, right? There's no real learning in the sense of us being able to then probe those weights and say, why exactly did we determine that this was this species of flower versus that one? Being able to more symbolically and algebraically explain why certain decisions were made and so on is currently a blind spot that we don't really have a reliable solution for. So that's definitely something that's going to need a lot of work as well. So I think the main next steps when it comes to ML research, I guess short term, are being able to scale efficiency, being able to explain, and also multimodal models are very interesting. So what that means are models that are not just understanding language, but are understanding like language, images, or text, images, audio, all in a single model. That gives you some really great capabilities. You've probably seen GPT-4o, which has its advanced voice mode and image generation and being able to understand text all in one model. It really is incredible just how well it performs in real world scenarios. Longer term, I'm also more interested in things like the intersection of biological computing with AI and ML. Like, for example, there's some companies that are working on experiments and research around literally culturing like nerve cells that you can work with to like train them to do things like fly a flight simulator and like play video games and stuff. And on one hand, there's obviously ethical discussions that need to be had about that. But at the same time, from a raw like potential standpoint, it is really interesting because they're significantly more efficient, obviously. They're also significantly faster at learning more complex tasks because they're biological. And so I think that'll also be an interesting area of research, but that's like more far future stuff, not short term. But yeah, I think those are some of the most interesting frontier areas of research.
Also, I have a personal question. So, in the university, I major in computer education, and actually, I think it's really similar to your career because you're also interested in educating about the computer. So, like, I want to ask you about what you think about the education for the teenagers, because like AI is very controversial. It's really good, but it could be also bad for the development. So I want to know about your insights about what the major things that we have to teach to the teenagers as a computer educator.
Sorry, lights just turned off there. But yeah, no, I guess, I mean, first of all, absolutely. Being able to share what I learned about tech is something I've always been really passionate about, and so I appreciate you breaking that up. I think, sorry, I missed the last bit of your question there. Could you just repeat the last sentence?
So like, I want to know, like, is it okay to teach them about AIs, or do you have to be really careful about approaching it as a teacher?
Got it. I think there's two angles to this. One of them is whether or not you should, and if so, how, teach them about AI itself. But then the other one is whether or not you should allow them to use AI in education. When it comes to teaching people about AI, I think that's like definitely like we should definitely be teaching people about both how to use AI powered tools most effectively, and the best way to do that is by giving them experience and sort of making it something that is part of their workflow, and also teaching people like how the underlying fundamentals behind this technology work, because only by understanding those fundamentals will they be able to then leverage it and sort of build and innovate with it in the future. So I guess on that front, I don't have I don't think that those opinions are too controversial. I think it is important to teach people about AI. I think the more controversial one is whether or not they should be allowed to use AI in the actual education process, and that is where things become a bit more of a gray area. And I think it's too early to say exactly how it's going to be integrated. But the thing about AI is that, like, the cat's out of the bag. Like at this point, we're not going back to a world where we don't have ChatGPT. And if we just tell students, no, you can't use it, or you can't use AI powered tools, it's sort of counterproductive, because like in the real world, they're going to use it because that's the point. And also in school, they're still going to try and find a way to use it. But if you are open to allowing them to make it part of their workflow in a way that is productive and not harmful for education, then I think it can actually be helpful. I have quite a few friends actually who use ChatGPT for a lot of their school work. But the thing is, they've managed to actually integrate it in a way where instead of it doing the work for them, it has instead allowed them to gain a deeper understanding of what they learn, because it's not like they never wanted to learn. That's sort of the entire point. Like they are interested in what they learn, but it's that they've never had physically the bandwidth or like the resources and the time to be able to do it, because there's just so much. And so their learning ends up becoming either just rote memorization, or they just don't have the time for it all. And so they're just not, they're unable to perform well at it. But when you have the tools to do things like just instantaneously demystify like confusing wording of things, or to be able to answer very specific targeted questions and misunderstandings that you have about things reliably enough, then suddenly, instead of you having to just memorize things raw or not being able to perform well, you have this third option of like this very like accessible, scalable, on-hand tutor that can just help you figure things out and understand them better. So I think we're not going back to a world where these tools don't exist. We might as well adapt to being able to make it part of education in a way that is productive instead of counterproductive. But at the same time, I think there's no good answer as to exactly how best to approach that today. That's still something that I think the entire community is still figuring out. Which, I mean, by the way, one more thing as a quick side note that I wanted to mention, now that you brought up educational resources, as a quick side note, even though I know we're a minute over. One of my friends was visiting Korea recently. He's from South Korea, and he went to a bookstore. And one of my favorite things to do, I mean, in general here in Canada, when I'm at different bookstores, is to go to the store and to see if they have a copy of any one of my books there, because I've written for tech books and a bunch of different interesting topics for around like programming and ML, and it's really fun to see the copies of that. I love sort of doing that. And he sent me a picture from Korea of a translated copy of one of my books on the Go programming language there, which was really exciting to see. So if any of you ever get the opportunity to see one of those in the wild and see a picture, feel free to, if you take a picture, feel free to send it to me. I love that sort of thing. But I mean, no, I love creating educational resources for all this sort of stuff, because I think it's really important. And only by actually understanding all of this and by having the resources to understand all of this will people be able to make productive use of it. So I think it is really crucial.
Is there anyone who has question? 질문 있나요?
What do you recommend for a freshman that wants to be a ML engineer? What do you recommend for them? First thing they should learn.
So I guess really, I might actually ask a follow-up question. So in terms of what you want to do with ML, would you say that you're more inclined to work on the software end of ML, on the mathematical end of ML, or on like the application? Or are you not sure yet? Because it's okay if you're not sure yet. That's fine. But I'm just wondering, do you have an idea of where you sort of like are naturally inclined yet?
I guess the software part of the ML.
Nice. Okay. That's actually how I started as well. And I ended up sort of naturally gaining enough of the mathematical intuition as I went along. But I still actually don't specialize primarily in the math behind ML. I am also personally still mostly on the software end. And I think there's two things I would recommend. First of all, it is surprisingly very important to have a really strong software background for ML. And the reason I say that is because there's almost like a joke in the software engineering community that you can always tell when software and when code was written by an ML developer versus just a developer. Because I'm going to be honest, a lot of that code is sometimes not the greatest. I've been guilty of it myself. Whenever I write ML code, it's like I sort of just enter a different like kind of programming where it's like I'm not writing code for code. I'm writing code as like a means to an end because I need to do something. Because again, ML ends up being primarily, I guess, focused on the actual solution algorithm versus the code. But the thing about ML is that, especially these days, when you end up writing it in the real world, a pretty big portion of the challenge ends up being just how do you structure the software in a way that you can actually maintain and scale it over time with the super complex hardware you're running it on, super sophisticated data ingestion pipelines to feed your models, the way to actually implement the math itself in a way that's accurate. It is hard for me to describe just how many days, if not weeks worth of man hours are wasted just because, for example, someone will forget to negate a value somewhere. And so the math will be slightly wrong from what we expected it to be. And people will be scratching their heads over like, why is this math not working right? And so much, right? So having a good software background is really important. So even building things that aren't ML related at all, just giving yourself experience with building applications that you find interesting, or getting just experience working with random like side projects that you build from a software perspective will also help you with ML engineering a lot. But then the other one is that even if you start top down, so even if you start by, for example, building ML applications by calling like the Google Vertex Studio APIs and like using Gemini or, the OpenAI APIs and things like this, where you're not actually doing the ML directly, but you're using ML services, doing that top down is good because, again, A, it gives you software experience, and B, it gives you a good intuition for what ML is capable of without needing to do the ML. But even if you do it top down, you want to work your way back down or even start bottom up, trying to understand the fundamentals behind the technology through examples that don't try and play into the hype of the tech. There's a lot of resources online that are like that try and use too many buzzwords, I find. Like one of the things I complain about is that since the release of ChatGPT nowadays, when you Google machine learning or you Google AI, you no longer get research papers and stuff. You get a bunch of people trying to sell you like prompt engineering ebooks and stuff like that, right? And so you want to try and steer clear of for lack of a better way of putting it, like the snake oil of the AI world, which is kind of hard. But find the resources that focus on a lot more of the fundamentals, that focus primarily on machine learning rather than AI. In particular, two resources that are really nice are Coursera. Coursera has some really good courses, and also cognitiveclass.ai. I can actually put that name in the chat if you'd like. Cognitiveclass.ai is one, and I'll also put in the GitHub link that I promised as well. Those two resources have some pretty good courses that start bottom up, and that will help you get a good understanding of a lot of the sort of, I guess, core constructs behind ML as well. So hopefully this was like a good start, this workshop, to being able to enter that. And of course, if you have any questions, my contact, it was on the last slide, but hopefully you can share contact with the folks that are attending, and feel free to reach out to me. I try to help out as many people that reach out with their questions, and hopefully I'm able to help out as well if you have any more specific things. But that's how I'd recommend starting to go about it.
Okay, thank you.
No worries. Thank you.
And now I think we can conclude today's session. Thank you, Tomei, for preparing today's lecture. You can leave
Thank
now.
you. All right. Have a good day, everybody. Thank you.
Thank you.
Bye-bye.